Hello and welcome to today's SEI webcast, Practical Use of Multicore in the Army and Beyond. We got a great crowd here already. I see people from Austria, Canada, Alabama, Washington, D.C., California. So we thank you for taking the time to join us. My name is Shane McGraw, Outreach Team Lead here at the Software Engineering Institute, and I'd like to thank each of you for attending. Our webcast today will cover four things: the technological backgrounds of multicores and real-time systems, the general experience that the SEI has over decades and our lessons learned, and a recent research project that the SEI has executed, and the transitioning of those results to the United States Army. We want to make our webcast today as interactive as possible, so you can submit your questions in the YouTube chat area now, and we will get to as many as we can after our panel discussion concludes. Our featured speakers today are Bjorn Andersson, Dionisio de Niz, and William Vance. Bjorn is a principal researcher here at the Software Engineering Institute. He has worked on multi-core processors before the word multi-core processors existed. They were called chip multiprocessors prior, and he has continued researching in this space. Bjorn, I know we wanted to be in person to do this, but glad we're able to do it virtually.
Thanks for the introduction, Shane. So I'm here in Pittsburgh in my office, and I look forward for great conversations.
Terrific. Dio is a principal researcher at SEI as well. He's the technical director of the Assuring Cyberphysical Systems Directorate. Dio, thanks for joining us and sharing your expertise in this area.
Thank you very much. I'm very happy to be here and excited to show our results and our collaboration with the Army.
Last but not least, we have William, who's a computer engineer at the U.S. Army Combat Capabilities Development Command, Aviation, and Missile Center in Trivector. He has been involved in the creation of guidance for the use of multi-core processors for Army aviation. Welcome, William. We're looking forward to you sharing your experience with the SEI.
Hi, all. It's good to be here, live from Huntsville, Rocket City.
Nice. All right, let's start our discussion. We have seen that multi-core processors have become increasingly important, and the timing is extremely important. Bjorn, can you talk about multi-core more in the DoD context and where timing requirements come from?
Sure. So let's look at this slide here. And you're seeing on the top left quadrant that there are different DoD systems, different platforms that they move in the physical world, and they should have an effect on the physical world. So they interact with the physical environment. And how is this achieved? It's achieved through software. We call these cyberphysical systems. And in order for the interaction to work well, the software needs to satisfy real-time requirements. So this is a general challenge for all sorts of systems in the Defense Department, the general purpose technology. We have also seen these public statements about this challenge from some entities, and here's one that you see below on the lower part of the slide. It's a statement from the former director of AMERDEC, now it's called AVMC. He points out that time requirements is very important. We want to use multi-cores, and that's a big challenge right now. But here we see just some pictures of examples. Now we can ask, what do these systems have in common? Can we form some sort of common view of these systems from time perspective? And I'm moving my next slide, but it doesn't work. Yeah, here it goes. So here we see it. So on the top here, you see a computer and you see a program executing on the computer. And then the program, it runs a while loop, infinite while loop, and reads the sensor, performs computation, activates a command, and it keeps doing that over and over again. And then you see a sensor in a physical environment. The program gets information from the sensor gets information from the physical environment. And the program sends an actuation command to the actuator, which influences the physical world, which in turn influences the next sensor reading. So it keeps doing that over and over again, and you see these arrows in the cycle. Then even lower part of the slide, you see events. You see a timeline, the time progression from left to the right. And then there are events. Read sensor, that's one thing that the program does. And then it actuates a command that's based on the sensor reading. And then it reads the sensor again. And then it actuates a command again. And the second one, it actuates a command, it's based on the second read sensor. And then we can start to identify time requirements here. We can see this arrow with the word period. From the reader sensor on to read the sensor again, that's the period. And then the reason why this matters is that we need to if you don't read the sensor very often, then we've had a bad picture of the environment. So we need to read the sensor often enough. And often in DoD systems, we express these things in terms of sometimes in hertz. So an activity needs to perform with 50 hertz, then it means that software needs to execute with 50 hertz, need to do this read sensor 50 hertz. That translates to a period of 20 milliseconds, for example. So we need to have a small enough period so that we can get a good picture of the environment. Then we also see the deadline here. That's a requirement from the read the sensor to actually into command. And then if that would be very long, then it means that we are acting based on old news. We are sending actuation commands based on some sensor reading we had in the past. It can be a long time ago. So that's why we need to have a short period, and we also need to have a short deadline and a long period. So short deadline and a short period, and we actually need to meet those time requirements. And it gets more complex because often we do not just have a single program, we have multiple programs under execution, and we call them threads or processes. So now we end up with many events like this, and you see them color-coded with red and green. So between these red and green, there is execution on the CPU. Now this execution, request of execution, that gets interleaved. So we end up with a problem of how to share the CPU. And there are other resources as well. So that's a challenge. So you can ask, why is it so challenging to satisfy these time requirements? If it was easy, then we wouldn't have to do this talking. We wouldn't have to do any research. We wouldn't have to develop any new solutions. So one way to answer this is to reduce the question to another question, which is what causes a delay of software from its request to execute until it finishes execution. So here we have a simple scenario. Often we have many threads, and the thread will arrive many times. But in this illustration, the thread only arrives once. And it has a deadline. So you see here to the left, the time when the one thread in the software system arrives, and then its deadline associated with that arrival. And one scenario is that it starts to execute immediately when it arrived, then it finishes. And there are different paths of execution, typically in these imperative programming, programs written in imperative programming languages. So this is one example. But there can be other inputs, and there can be other states that cause the program to execute another path. And then it will have longer execution time. And it can also be that this thread, the blue thread, it got preempted. And you see that here. Here is some time when the blue thread doesn't execute, and it is because another thread is using the processor core. And then it executes blue again, but then the blue thread requested a critical section, and then another thread held the critical section. So then the blue thread cannot execute. So here we see three reasons why it is a delay. There is the thread's internal execution. There is preemption from other threads. There is a critical section, and there are other reasons also. This is a very simplified view, but it gives an idea of the factors that influences delay. And when we want to have correct timing, it's not just that we want to, when we mean that the finishing time should be smaller than the deadline, and here we did that, and here we did that also, but we would like to make sure that for all scenarios that we assume can happen, the finishing time is less than equal to deadline. So there can be a very large number of possibilities. So far I've just talked about single core, but we're focusing here on multi-core, which makes it more challenging. And today, almost all computers are multi-core. Most shippers don't even offer single core. And we'll focus here on shared memory multiprocessor, meaning shared resources, shared memory, but also shared address space. And so the problem we're facing is something like this illustrated here, where we have a set of processes or threads assigned to cores, and then we have they contend for resources within the core, but we also have a memory system with resources. And so now we can have contention for resources in the memory system from two different threads on different cores. And this is the situation we face. And we want to have, the problem we have is, for each problem statement is for each process, compute an upper bound on its response time. Response time is the time from which request to execute until it finishes, until it finishes the execution. If that's less than the deadline, then we're good. So in order to illustrate this further, let's call it this scenario when we have 3 cores here and just a single thread on core 3. And it may arrive and then it executes full speed and it finishes. And that's a sunny case scenario. That's a good case. But then there can be other scenarios. And here's one of them when there's execution on the other process cores. And you see the green and the blue and the dark blue and the brown here. When they execute another course, they will request resources in the memory system. That causes contention for resources in the memory system. That causes slowdown on the red one. Then the finishing time is later. And here we're still lucky because the red one didn't get any preemption. But we can see here different scenarios cause different finishing times, and that can happen with multi-cores. So as I already mentioned, these shared hardware resources, they impact the timing. And we want to make sure that for all scenarios that we assume are possible, the software satisfies the time requirements. And how bad is this? So it depends. It depends on the hardware, it depends on the program, but it also depends on the particular scenario we are running or the scenarios that we are consider are possible. So in some cases, it's not so large. In some cases, it is larger. So there have been investigations in literature about this. And one of them, as you see in the second bullet, that the literature mentioned that we can have 103 times slowdown. And there's actually been other reports that show 300 times slowdown and 1,000 times slowdown. There exists hardware and there exist programs such that there exists a scenario when you can have this very large slowdown. So one challenge we are facing, it has to do with undocumented resources, that we are trying to prove a property of a system, or although we don't know, that depends on the arbitration and resources, and we don't fully know how this arbitration is done, and we don't know exactly all the resources that exist, and that's a big challenge. And even if we know resources, there has been some work to try to model these resources, but the literature is very limited. It only models a small number of resources. You see here the picture to the right, some resources, but this is a very, very simplified view. There are many, many other resources that are not shown here. And this problem is getting worse. We are getting more slowdown and we're getting more undocumented hardware. And why is that? It's because we are seeing more and more cores per chip. And since we get more and more cores per chip, we get more and more threads connected in parallel. And if we have more and more threads connected in parallel, we get more and more memory access per time unit, and we get more and more memory access per time unit. We get more and more pressure on the memory system. The queues are building up, and then we get more slowdown. It's also the case that since it gets worse, the chip makers tend to implement more and more features to deal with this. Chip makers have more levels of cache, more write-back buffers, more prefetchers. So that's why we get more hardware that's hard to analyze, and some of them are undocumented. So over to you, Shane.
Bjorn, thanks for that great kickoff. We appreciate the overview. Let's bring in William here for this question. Can you speak to the specifics related to the Department of Defense, how your organization works with Multicore, and how you see SEI's work in this space, using the research results playing out and playing a role in the DoD?
So our collaboration with Dio and Bjorn has gone back to our Multicore workshops that we've had in the past. This type of collaboration among academia, industry, the DoD has been instrumental for us developing our requirements and giving guidance to Army programs.
Okay, let's move on from there. Dio, let's bring you in. Can you say something about what led to Multicore in the commercial industry and why the chip and computer industry is focused on it?
Sure, let me try to share it now. Let me see. Well, I guess that somebody else is sharing. That may be Bjorn.
No.
Got it. Okay, so very briefly, I just wanted to point out to these slides here. In particular, one of the challenges in the industry that brought up the multi-core era, if you will, was actually what is called the power wall. So it means that as the processor manufacturers, in particular Intel, were trying to create faster and faster processors, they run into the problem that in the last iteration they have in 2004, the project was to create a processor that will run at 7 GHz. But the problem is that the power, the dissipation that was creating, the power consumption, if you will, was way too high. And it proved to be impossible really to tackle this problem, right? So in fact, this project was actually canceled. And that created the new kind of, I would say, trend to add more cores, starting with the dual core processors, if you will, right? But later on in 2007 and 8, Sandia Labs discussed the new challenges, that is the memory wall. So what it means is that you have a collection, a set of cores that will access shared resources, as Bjorn already pointed out to. And in particular, when you keep increasing the number of cores, the interference that the cores will do between themselves will actually create more and more delays. And in the traditional way to do the access to shared memory in particular, at that point in time, the problem was that the delays were so bad that even getting to 8 cores, the performance started to decrease. And getting even to 18 cores was actually worse than just having 1 core. And as you will see, this kind of it's a tough problem to tackle. Fortunately, I will say the industry has been able to work out these solutions partially, right? So, and I'll tell you why this is a partial solution. So instead of having, as we mentioned before, a single core with a lot of power, we parallelize the workload, put it into a kind of, I would say, not as fast cores, but multiple of them. And we have been able to reach some reasonable numbers, if you will. For Intel, for instance, one of the examples, we have 40 cores and 80 threads. And for AMD, 64 cores and 128 threads, right? So these are really a large number of cores now, if you will. But the solutions they have been able to do is based on throughput. So it means they allow you to improve the average case execution time. But unfortunately for real time, that's not the figure that is the most important. Bjorn mentioned that we need to meet deadlines. And these deadlines are based not in the average case, but in the worst case. Otherwise, it's not possible to really provide any guarantees, right? So, and part of the problem as well is that the hardware solution that has been designed for throughput actually hinders the predictability of the worst case execution time, right? And that also makes the analysis more complex. And as Bjorn mentioned before, sometimes they want to keep these mechanisms protected because of intellectual property, and that creates even more challenges for the analysis itself. We'll get into more details later on. Back to you, Shane.
Great. We're going to go back to William. We're going to give him a chance to share a couple slides from that previous question. We had a little hiccup. So he's going to talk about how his organization works with Multicore and how he sees SEI research playing out. So let's turn it back over to William for that one. William?
Thanks, Shane. And so I work in the Multicore Lab, giving guidance to Army programs as they transition from the use of single core processors to multi-core processors for added capability. So let me go into a little bit of our history. So we started researching the problem space. Well, actually before that, Jeff Lengout, the acting director at the time, he saw the need for multi-core for the added capability that it offers in terms of size, weight, and power. So when we first started, we researched the problem space that involved building a database, which I'll go into in a minute, of white papers, good quality academic research papers, and reading the various standards that are related to the use of multi-core in aircraft. This pertains to DO 178, DO 297, the use of hardware and software on avionics on aircraft, and also the CAS 32A paper, which was written by the CAS Authority. That was a collaboration between the representatives from certification and regulators, FAA, EASA, and we took that guidelines, it's not a set of requirements, and we developed our requirements for the use of it in the Army, use of multi-core in the Army. So that's pretty much our start, and we developed a set of requirements, and we received comments from SEI on those as we refined them. And in the lab, we perform interference analysis, and we target multi-core hardware with applications to study effects that are that occur when you share resources, co-running applications on separate cores. So we give methods of compliance to Army programs for the safe use of multi-core in aircraft. So Let me go into that knowledge base that I mentioned earlier. In this knowledge base, we have a large set of research papers, and those are linked back to our requirements and the various standards that I mentioned. And for each one of these objects, we have a summary that a team member has written for it, and we have comments on it, and all that is traced within our database. And this has been fundamental in us cultivating a multi-core expertise. We give, as I said, we are the multi-core experts for the Army. So some of the issues and challenges with multi-core is that whenever you share a resource, there are interferences. And what I mean by interferences are that a core affects another core's execution time through the use of shared resources. This concepts such as serialization come into play, eviction with cache, bandwidth of buses, and this makes it hard to achieving a deterministic system and understanding and capturing the worst case execution time, because there's multiple cores running and different metrics firing off, and that problem just explodes as you add more and more cores. So this is where the role of accreditation and certification comes into play. That's why I mentioned we put together a set of multi-core requirements for doing it safely on aircraft, and determinism is the key to safety and security. So this is our set of requirements that were later codified into our larger set of our AMAC, our largest set of airworthiness criteria. And this was public release. We sent it to Dio and Bjorn for their review, and they contributed and gave feedback on it. Something else that emerged from our collaboration, we do biweekly working groups, and we put together a interference matrix. When you're doing interference analysis to understand the behavior of the multi-core system, you have the various resources, and often there's an issue associated with the use of that resource. Even if it's private, for example, with local cache, this first row, that issue may not be multi-core at first thought, but an issue can propagate from a single core problem to a multi-core problem. And you have to perform analysis on the resources, target them specifically. Sometimes with applications, we have a set of tools for performing interference analysis. We have a GUI, and we have what we call red apps and blue apps for performing interference analysis and affecting a baseline's application's performance by adding more additional cores. And in addition to analysis, you have a mitigation for, you see the problem, you have to say, how do you bound the interference impact that you see there? And there's different strategies depending on the resource, and the success of these strategies are going to vary when you're going to different multi-core architectures. And you have to verify that you didn't break anything when you apply those mitigations, and that it's behaving in a more deterministic way. So I'm going to go through a few here. I don't have time to go through all, but I'm going to touch on, for example, you have cache coloring as a mitigation strategy for shared cache. You have temporal isolation as a strategy for shared devices or AIO devices. That would be running something in its own time slice so that there's interference isn't an issue, multi-core interference, since there's just, it's effectively acting as a single core. And I'm going to go in a bit, I'm going to go over why scheduling is so important. But first, I'm going to touch on an example of interference and how it can occur. You see here, you have these individual caches. This is on the, well, this example was on the P4080, but for this diagram is a 4-core system where you see an interference occurring in the caches. And this is one of the more glaring interferences where you can have evictions out of cache, which would go into main memory, and it goes across a shared interconnect. And you also have cache coherency coming into play, where keeping the caches recent with all copies of the same data. So this is one of the tests we performed where you see the baseline case. There is this violin plot. The worst case would be at the top here, at the tail end of it. And you see that tail end, it gets more and more undeterministic as you, non-deterministic rather, as you add additional cores, and you see the standard deviation going up through the violin plot spread going up, and you have to mitigate that through some configuration, or that may entail running something by itself in its own time slice, or some of the other strategies I mentioned on the last slide. So I'm going to go into some of the tools, specific areas of collaboration that the Multicore Lab has done with SEI over the past. This first tool is a genetic algorithm tool. So genetic algorithms, it involves often a mutation stage, splitting of genes together and splicing those. And this was used for determining the worst case input into an algorithm. For here, it was just a simple bubble sort algorithm where we had a set of parameters in my conf configuration, and it was given into this tool. And so we ran this tool, and it arrived at this worst case execution time. So this has value in that characterizing the worst case execution time is one of the major areas for proving determinism to a significant, a satisfactory extent of your safety. So this was the worst case input that this was what was determined to cause the worst case execution time. So this is the input into the bubble sort algorithm that would produce that worst case execution time. Another significant area is scheduling. Scheduling is one of the key ways in which you can do mitigation and sometimes even eliminate all of your interferences by co-running applications with low interference impact, and at times where there's a high interference, minimizing the number of co-running cores. So this was based on some of the research that I mentioned that we have incorporated into our database. It's from Bjorn's paper on schedulability analysis of tasks with co-runner dependent execution time. And we evaluated this, and we see the value in that as you add more and more cores, the challenge and the number of combinations in which ways you can schedule your system increases. So we use this example task set and performed schedulability analysis. And that was all documented in our database, and it's going to play a role in some of the guidance we write in terms of scheduling applications. So going forward, what I see is that you have this extra processing power, size, weight, and cost, power, all that savings you can, capability you can gain from adding additional cores. And this is where the multi-core has its role in guiding Army programs and how to do it safely and thoughtfully. And most important is the safety. So we've collaborated in the past through workshops. We've done bi-weekly meetings, as I said, in between workshops. And I'd say watch this space in the future as we collaborate further with industry and academia. So it's going to be most beneficial for the success of the warfighter going forward, supporting, as Bjorn said, additional sensors and actuators, to name a few. Back to you, Shane.
Thanks, William. Bjorn, one thing I wanted to mention earlier, you mentioned undocumented hardware is one issue. Could you touch or follow up on that?
Yeah, so that's a big issue. So you saw in my presentation this paper from 2015 when 103 times slowdown. So that was caused by a resource called misstatus holding register. And at that time, before that, I actually didn't know that there was such a thing called misstatus holding register. And I used to talk to a lot of people in the research community, and no one mentioned that. And I don't think many other people knew about that either. So it was kind of like, of course, people build the hardware knew about it, but the people who do analyzing timing didn't think too much about misstatus holding register. But it had this 103 times slowdown and actually worse effects. So that was kind of scary. There is a big resource that we haven't thought about at that time. And then that also brings this question, maybe there are other resources that we haven't thought about that we are not aware of. More of these unknown unknowns. So that was scary. Another part that makes it a bit scary was that we sometimes want to apply mitigation strategies to reduce the intercore interference. For example, when we have caches, then we can use something called cache coloring and other techniques. But for this misstatus holding register, right now there is no mitigation strategy for it. So there was something we discovered 7 years ago, and it had a big impact. There's no mitigation strategy for it so far. So yeah, that's been an issue. Thanks.
Great. Let's bring Dio back in, and Bjorn, feel free to chime in on this question as well, but we'll start with Dio. We know the SEI has created many solutions that address the timing of software executing on Multicore. Can you guys talk a bit more about that?
Yes, so let me use these slides to go over a few points. We have already been discussing these shared resources, and some of the techniques have been mentioned, like coloring. So let's go one level of detail deeper. So the reason why kind of shared caches are a problem is that cache is actually a fast memory that is used to hold the most frequently used data that we want to access. So, and that is divided into different sets. So when two different cores read memory, they will load up, let's see, the content of the memory in the cache to have a faster access. The problem is that if they kind of load the data into the same set, then what we will see is an eviction. Exactly what at some point in time Will was mentioning, and that becomes a problem, because then every time we do this eviction and replace the memory, the next time the other core accesses the memory, it will suffer a larger delay. In this particular case, we are talking about an order of magnitude larger delay, that if it's still small, it accumulates and actually reduces significantly the performance of the system. So the solution typically, as has been mentioned before, is called coloring. So coloring, basically what it means is that we make sure that the memory that is accessed by one core is not loaded into the same set. So in this particular case, and they are called coloring because you say you assign colors. So for instance, in this particular case, core 1 will only access memory of color red. And therefore, if we keep the colors separate, core 2, for instance, uses color green, then they will not replace each other and the interference is eliminated. That is basically the coloring technique, if you will. And this has been used in the industry, and we have used this in our papers, right? But once you start kind of combining multiple of these resources, so we talk about cache, but once you go down to RAM memory, then you need to play other type of interference of what CAS22A will call interference channels, right? So what happens in the memory, in the main memory, this is organized in different channels, different ranks, and in each of the chips, we will have what is called a memory bank. The memory bank has also its own cache, if you will. That cache is called the raw buffer, because what it does is just kind of loads up a collection of columns that you will access one column at a time, so that you can have a faster access to this memory. And for instance, one of the challenges here is not only that you can replace the raw buffer that is exactly as cache, but also when you try to improve the sequential reading, what the memory controller will do is it will order the memory accesses in terms of the row that is accessing. For instance, in this particular case, if we have an access to row 1, right, one of the problems is that if I let it on a second core, we'll try to access row 2, right? And it will kind of add into the queue of accesses in the memory controller. The memory controller will see that in order to maximize the speed, it will take advantage of the buffer that it already loaded, that it was the buffer of the row 1, right? So it will actually reorder the accesses in a way that it will favor all the access to row 1. And that will be very good for the core 1 because it will speed up the accesses, but it will delay the accesses of the core 2. And it will make the worst case access of this memory worse, right? So now with all of these different mechanisms, we need to find a way to model all of them together, right? Typically, one of the solutions for this is also to apply coloring as well to memory banks. In the same style that we did for the coloring of caches, what we will do is we will divide the memory into memories of different colors that access different banks, right? The problem then is that once you have together the cache coloring and memory coloring, then the problem is that we are going to be using the same techniques to be able to do this. And these techniques is basically, when we implement this in the OS, we are trying to manipulate the address bits to select a certain cache set or a certain memory bank. And that actually creates actually a conflict. As you can see, we are using for the cache color index these bits, but those are also reused for the bank color. That conflict, in fact, creates additional problems that we need to resolve and have a coordinated solutions for both of them together, right? And of course, there are other problems and other type of shared hardware, like the I/O when it does the direct memory access. Interestingly enough, this is not only a problem for multi-core because it behaves as yet another core, creating interference, but actually this problem exists even in single core, when the single core has input-output that uses the direct memory access. And the other kind of significant, I would say, interference channels is the translation look-aside buffer that is basically a cache to kind of have a faster access to the virtual to physical page translation in virtual memory, right? And so all of these are actually the problems we need to address. And our solutions actually create analysis and configuration algorithms to be able to kind of create combined solutions for all this. Back to
Bjorn, anything to add there?
Yeah, so as both Dio and William mentioned, we have this shared cache between cores, and the one mitigation strategy is to apply cache coloring. And that works, that's good when you can do it. But we also have these undocumented resources that I mentioned. Misstatus holding registry is one of them, there are many others. And then you can ask, how do we deal with that? We don't have mitigation strategy. Could we somehow model that and model the request there? Well, we don't really know how that works either. So we can't actually create a method to analyze the complete worst case delays either, one may think, if we try to model this, because we don't know exactly how, we know it exists, but we don't know exactly how it works. And there might be other resources as well that we haven't found yet. So how can we deal with that? So one idea that we had recently in our research was that maybe instead of modeling the resources and the access to the resource, we model the effect of the resources. Slight difference. So we don't actually need to know that it exists. We just need to know that it does something. And then our idea was that we can create a model where we describe a thread, the speed of execution of a thread, as a function with co-runners. So we don't actually know that either, because it depends on lots of circumstances. But what we can do is that we describe the speed of execution of a thread as a function of co-runners, but we describe a lower and upper bound on that. And then if we have those bounds, then we can feed that into a formal analysis technique that can prove deadlines. And then that's one approach. But then you can ask, how do we get those lower, upper, and lower bounds on the speed of execution because they depend on a resource that we don't know how it works, and they may depend on resources that we don't even know they exist. How do we deal with that? So what we do is that we do empirically. We run tests with one thread, another thread as a co-runner. Then we see, we run many tests to try to stress it, to see what can be lowest speed we can observe. So that's, run tests locally to obtain parameters. Then we can feed those parameters into a formal analysis technique. So it's a combined approach with empirics on a low level and formal methods on a higher level. So that's one way to deal with that.
All right, let's bring William back in for another question. What happens, William, if we stick to a single core? What are we losing or what are we missing?
When you stick to a single core, you lose the added capability. That's only really possible with multi-core. We've pretty much pushed the limits of single core. And in order to support additional sensors, actuators, visual systems, navigation systems, the number of sensors, the number of chips, for example, that are going on your car are increasing every year. The same thing's true for aircraft. In order to support these added capabilities, you need multi-core. So without it, you lose all the added capability that comes with it.
So with that, what happens in the future, William? I know you can you see into the future? Do we use more or less multi-core?
Core is pretty much clear. They're no longer making single core. What's traditionally been done is to disable all but one core, and there's different ways to achieve that. But in short, we're going to be using multi-core in the future to support all these added capabilities I mentioned, and as Bjorn and Dio have mentioned.
Next up, to follow up with that, William, you listed some DoD programs that use multi-core. Can you talk more about that and how they're using it and what challenge you see there?
A number of years now, maybe even decades or longer. So just bridging the gap there, and for programs, there's a lack of experience, for lack of a better way to put it, of programs using multi-core and also with the certifiers. So we're in the growing pains stages there with developing, well, we have our requirements pretty much figured out, but developing the methods of compliance that are used to satisfy those requirements, what needs to be shown. Bjorn talked about the different approach with using an empirical strategy, or you can use other strategies where you're collecting metrics and trying to get a deep understanding there of what's going on. So just I would say probably the growing pains, to put it simply, of using multi-core.
Great, Bjorn, question for you. And this is something I've heard, over the years being at the SCI. There seems to be a difference between practitioners and academic research. So can you elaborate a bit on that for us?
Yeah. So there is also some similarities. So one similarity is that both industry and academia, we both care about building safe system and that can interact with physical environment. So in that sense, I think we're in good alignment. But there is a difference, and that is that academia tend to focus a lot on creating models of systems and then proving properties of those models. And sometimes there are free parameters that can be configured to get better performance. And sometimes configure it so that the proofs go through. So there are some cases when you have configured parameters, if you configure a system in one way, then it's actually impossible to prove it to meet deadlines. But if you configure a system in another way, it is possible to prove it to meet deadlines. For example, priority is one example of such a configuration parameter. How you assign threads to process cores is another example of things that you can configure. So that tends to be the academic view. Model a system and then try to configure it in a good way and prove that you satisfy time requirements. In industry, some people do that too. There is a little bit of that way of thinking in industry, to model a system and try to prove that you meet deadlines. But there is also a strong focus in industry on building the system for low variation in execution time and running tests. So building, for example, you can design a system so that response times of jobs, they don't vary so much. And then there is smaller set of possibilities, and then applying testing. So testing works better if you have less variability. So that's an important difference between industry and academia right now.
Let's go to Dio for this one. Dio, can you talk about whether these techniques are useful for independent verification and validation and certification as well?
Yes, actually, for instance, as Will has mentioned previously, there's a number of certification standards, including also the guidance that Will's organization created, right? That they talk about how to use these techniques, the goals of these techniques, right? For instance, CAS 22A is a guidance that talks about identifying all the different interference channels and how to really kind of relay the different mechanisms to have mitigation. And also, once you mitigate what is possible to mitigate, you also need to have some sort of analysis that will tell you and prove, for instance, that we will meet deadlines, as Bjorn has said in the past, even for those techniques that for which you don't have mitigation.
All right, leads us to kind of a wrap-up point for each of you. So for each chime in, what needs to be done moving forward? So let's start with Bjorn. What's your comments to that question?
Yes, I think there are two things that need to happen. So one of them is that we need to have a shared language between industry and academia. And we need to be able to come together and recognize compatibility with different solutions, because no entity is going to solve or create all components. We need to have an ecosystem where different entities, different academics, different corporations, and other government entities can develop solutions, and then they can come together. And then we need to be able to know assumptions of respective solutions. And yeah, that's one part. Have a common have a discussion about this and come together. But then there are also deep scientific challenges, and that require also consistent effort. So we need to address those also.
Dio.
Yes. So, for instance, one of the important challenges that we need to address is for single core, there is kind of a well understood way to think about certification evidence, how to create certification evidence. But once we get into multi-core and things get a little bit more difficult to narrow down, we need to find out and have a deeper discussion with certification authorities on what is the shape of evidence that is useful and how to produce that evidence, how to make it practical for the practitioners, how the academia can actually develop these practical methods that produce the evidence that is required by the certification authorities.
Great, William, we're going to give you the last word to this question, what needs done moving forward, and we can tie in just, how you guys have used the SEIs and continue to do so in the future.
I think I'm in violent agreement with what Bjorn and Dio have said, with various parties, whether it be the regulators, the vendors, those performing multi-core on their programs, coming together for a agreed upon definitions, for example, standards, best practices. And there's a lot of there needs to be a lot more reuse of work and research that's been going on, so we can build upon and compound ideas there to come up with solutions for this space.
Great, thank you for that. This great discussion today, guys. So we're going to open it up to some audience questions. So we had a question from Todd, and I'm going to point this one to Bjorn. And Bjorn, if you're not the right, maybe you can pass it to the other panelists. But from Todd asking, what sort of rate monotonic analysis methods have been tried, and how do they help or hurt planning for multi-core?
So that's a big question. So first, we can talk about what is the meaning of the word rate monotonic. So rate monotonic originally was started in 1969 during the space flight program, for the program. And then they observed that if you have a set of processes or threads, then how do you assign priorities? You like to assign priorities so that it's possible to find a way of assigning priorities so that if it's possible to meet deadlines, you will meet deadlines. And then they proved that for a certain model, there's a person called Liu at the Jet Propulsion Laboratory in 1969. And he proved that there is a way of assigning priorities so that you sort the process in this descending order of their arrival period. So if a process arrives very often, then it has high rate, and then it has a small period. So you sort them in that. And then you give high priority to those with a high rate, and high priority to those with low, small periods. So then he called that rate monotonic. So that was the original, that's how the word came about, word rate monotonic. So we use the word rate monotonic in different ways, but that was the starting point of the word rate monotonic. So rate monotonic, actually, one meaning of the word rate monotonic is it's just a way of assigning priorities. That was the original meaning. It was shown to be optimal under certain assumptions. But then we can use the word rate monotonic in another way. And that came about later in the 80s, because people recognized that we have many real-time operating systems where we have fixed priority as a CPU scheduler, and then we would like to apply the rate monotonic priority assignment, that scheme from 1969. But then they also recognized that we do not just want to assign priorities, we would like to prove that we meet deadlines for these processes. And then they developed analytic methods so that you took a model of these processes and proved that they all meet deadlines. And then they realized that if we have analytic methods that use the rate monotonic priority assignment, then what should we call these analytic methods? Well, they call that rate monotonic analysis. So the rate monotonic can actually mean the priority assignment, that was the original meaning, and then people talk about rate monotonic analysis that came in the 80s. And then, that was in the 80s. And then you can ask, how does this work on Multicore? So there are a lot of issues in Multicore. One of them is this shared memory that we talked about a lot. But even if we didn't have all these shared resources in the memory system, there are still big challenges. Suppose a perfect memory system where there is no co-RAR interference, then we actually still have big issues because it turns out that if you go back to look at the proofs from the rate monotonic analysis from the 80s, there's a property that they rely on, which is that if you miss a deadline, then the single processor was busy before it missed the deadline. But on Multicore, even if you have a perfect memory system, it doesn't necessarily hold that if you miss a deadline, then all cores were busy. It could be that you actually miss a deadline when almost all cores were idle and just one was busy. And that's the one effect that was actually shown that's quite serious. So it was shown that with rate monotonic, if you apply that directly on a Multicore, there are different ways of doing it, if you have migration, no migration, and so on. But there is a number of results which show that there exist sets of processes where you miss a deadline, although the average process utilization over a long time interval approaches zero, and you still miss a deadline. The average process utilization approaches zero over a long time interval, and still miss a deadline. So the people have recognized that there is a problem with just there's some assumptions that can be a big drawback rate monotonic. So there have been other works on how do you use rate monotonic priority assignment and this rate monotonic analysis. So one idea people have had was that you use something called bin packing schemes. So you use a clever way of assigning test of processor cores, and then you treat each processor core as a single core. And then you apply a rate monotonic from the 80s on that. And then that is initially assumed there were no interference in the memory system. And then there are other approaches when you actually have fixed priority preemptive scheduling in the CPU scheduling operating system, which doesn't rely on rate monotonic. Because one can show that the rate monotonic priority assignment was optimal for a single core, but not for Multicore. So there have been other works, and I've been doing that avoids this issue. I mentioned that the severe thing that in certain cases, rate monotonic can miss a deadline, although we have arbitrary low process utilization over long time intervals. And there is a trick to avoid that. And I have a paper about that, and there's been other works later on. So I think the question was, what should we think about for rate monotonic now when we move to Multicore? And one answer would be, you can use a single core rate monotonic on each core, the way of assigning priorities. You can, if you don't have any core interference, you can use single core rate monotonic analysis also. You can use this extension variant of rate monotonic, which aren't rate monotonic priorities, if you have tasks with shared ready queue. Yeah.
Great answer. Thank you for that, Bjorn. We got about a minute left, so we're going to wrap up the last question. We're going to point this one to Dio, and then maybe let you have a closing comment or so. For Dio, techniques to uncover multi-core and virtualization related defects.
Yes, this is actually a very interesting topic, as sometimes you will think that using virtualization and kind of separate the different cores in different virtual machines perhaps is the answer. The reality is that even though that is a technique that could potentially give some advantage, we need to be very careful, because once we have virtualization, then you are not only dealing with one scheduler, that gives turns to the different tasks, but you are dealing with two schedulers nested in each other. So there should be very tight coordination, and that tight coordination also needs to be very careful about the shared resources, the access of shared resources. So even though it's useful, we should not think of this as just using an out-of-the-box virtualization scheme or the virtual machines that are popular and downloadable today, but we need to have the specially designed to make it work, right?
Great. That's about all the time we have for today. Bjorn, Dio, William, thank you very much for sharing your expertise. We appreciate the hour taking the time to be with us today.
Thank you very much.
Thank you.
Thank you.
And also, we'd like to thank you each for attending today. And we want to let you know the SEI is actively looking for collaborators in this area. So if you'd like to collaborate with the SEI in the area Multicore, please email info@sei.cmu.edu. For those of you looking for more information in this area, we have a number of resources on our website. Upon exiting, we ask you to hit the like button at the below of the video window, and we ask that you share the archive if you found value. You can subscribe to the SEI's YouTube channel by clicking on the SEI seal in the lower right corner of our video window. Lastly, our next live stream will be May 25th, and the topic will be Cyber Analytics with Thomas Scanlon. Registration information will be on our website soon and will be emailed out as well. Again, any question from today's event, please send to info@sei.cmu.edu. Thanks, everyone. Have a great day.